All right, we now need to talk about traits, and traits give a very specific view on the idea of object orientation. So the structures that we've had and the instances of structures that we created, they were basically collections of some fields and some behaviors as well in methods. But one of the things that is kind of interesting is to define relationships between the different structures. And the way that this is done in Rust is very unusual and it's quite different to other programming languages. So let me give you an example of how the whole thing works. Now let's suppose that we have a hierarchy, or we have several different types of animals in our system. We have humans and we have cats. Kind of like what's happening on Reddit. You have humans and you have cat pictures. So we have humans and cats, and let's suppose that they can both try to talk. Obviously, humans can talk and cats can just make funny noises and whatever. So we want to define this idea that both humans and cats share certain traits. And for that, you use a trait. So we're going to call this trait animal, and we're going to define some of the things that animals can do. So there's just two things that we need to define here. So let's assume that both cats and humans have names. So we're going to have a function called name, which takes a reference to self, and it returns just a string. So just an ordinary str. And similarly, what we're going to do is we're going to define a method called talk, which also takes a reference to self. And here is the interesting thing. Now, let's suppose that for some reason we didn't give humans or cats the ability to talk. Let's say we forgot. What we can do is we can provide a default implementation that a human or a cat would have. And this default implementation can be something like this. So we can say that this named animal cannot talk. Okay, and then we get the name. So self.name. All right. So this is our trait, and now when we define our classes like human or cat or dog or whatever, we can choose to implement this trait, thereby implementing these methods and letting them perform the talk action and returning the name as well. So let's take a look at how this would actually work. The actual structure for human, for example, would be very simple, because essentially all you have to do is give the human a name, because that's what we're going to return through the name method. So here is the name method, and here is name as just, a static str. So nothing special here. But what we can do now is we can take those traits which make an animal, and we can say that the human is an animal, therefore the human is going to implement some of those traits. So we implement animal traits for the human class. This is how you do it. You write import animal for human. Okay, so now if you try to compile this, it's going to complain because not all the trait items have been implemented. You now have to implement at least the name trait. You'll notice that the talk method doesn't need to be implemented because it has a default implementation which you can override. But let's implement name. So name is actually easy because it's just function name reference to self, and it returns a static str. And sorry, that auto completes it to struct all the time. It's annoying. So here all we do is we return self.name. That's what the name is actually for. So the idea here is that essentially somewhere down below, like here in this traits function, you say let h equals human and give it a name, John, and this name would subsequently be returned from the function name. So we can compile this, and this already kind of works. Actually, it builds, and we can actually take John here, and we can say h.talk. And because we haven't given the human an ability to talk, but we have given the animal a default implementation, what happens is that's exactly what gets used. And so it tells us that John cannot talk. Now, of course, we do want John to talk. Therefore, in the implementation of animal for human, not only do we implement name, but we can similarly implement the talk function. So function talk self, and it's not going to return any values. What we're going to do is we're going to do a different print line. We're going to say that John says hello, for example. self.name. There we go. All right, so let's actually run this. So John says hello now. That's good. Okay, so we can do a similar thing for a different type, like for example for a cat. So a cat in our case can be very similar to human. I'm actually going to duplicate the entire thing. So the cat will also have a name, and then when we go to actually do the implementation, let's copy all of this and just import animal for cat. So it's, instead of saying hello, it's going to say meow. So what you can do is you can say let c equals cat, again with a name of, I don't know, Misty, for example. And then you can do cat.talk. All right, so let's run this, and you see that John says hello, but Missy says meow. So essentially, human and cat have different implementations of this talk method. All right, so this is good, and this lets us actually define kind of families of types which implement particular traits. So what else can we do? Well, one of the cool things that we can do is we can, for example, define the creation function. So let's suppose that we have a function in our animal trait, which is called create, which is used for actually manufacturing cats or humans or whatever. And we can also make this function static. So we're going to have a function called create, but notice it's not going to take a self. It's not going to take this as a parameter. And as it doesn't take self as a parameter, it means it's not an instance function, it's a static function. So we're going to have a function which takes a name, which again is just a static str, and what it's going to return is the type of the implementor, and the type of the implementor is called self. Okay, so we now have another thing in this trait which forces both human and cat to define a method called create, which creates an instance of human or animal. It's kind of like, you know, we had vector and we had vector : u. That's a factory function. So here is the thing. For human, you would have a function which looks like this. So you would have function create, which takes a name as a static str, and it doesn't return a self, because a self is an indication of the type that we're going to return. So if you're creating a human, you're obviously going to return a human. And the creation process here is very easy because we have the name, so we just assign that and return that. So we return a human with a name given by the argument here. Okay, and the same goes for the cat. So here we say function create where name is static str. Here we return a cat, obviously, and the way we do it is by initializing a cat with the given name. All right, so what does this mean? Well, it basically means that we can go down here, and instead of initializing the human in this way, we can initialize it in the following way. We can say let h equals human : create with the name John. There we go. Let's run this. Okay, so there's a bit of a problem here. We left a semicolon where there shouldn't be any because it's a return statement. So let's go again. Okay, so this is okay. John says hello, but now I want to show you something that's a bit amazing, somewhat cool in the Rust world, and that is that instead of calling on human, what you can do is you can call create on animal. You can call create on animal. Now, this isn't going to work the way I've defined it. In fact, if I try to compile, it's going to say the type of this value must be known, because as you're executing animal create, you are not sure what type you're getting because the type is actually self. It's defined on the implementor. When we did human.create, : create, that was obvious that we were making a human. However, look what I can make here. If I say human, then this compiles and works just fine. And this is pretty amazing because what's happening is the exact implementation of the create method is chosen by the compiler based on the fact that we're assigning it to a human, which is pretty awesome. Now, the last thing I want to show and kind of exemplify is this idea that you can add traits and you can add behavior to types which you don't even own, which you haven't yourself created. So let me give you a very simple example. Let's suppose that you have a vector of values. Let A equals a vector of elements 1, 2, and 3, for example. Now, let's suppose I want to print out the sum. So I want to print out, let's say, sum equals, and then calculate the sum of this vector. Now, this is a bit of a problem because obviously sum doesn't exist, so I can't just go ahead and compile this. However, what I can do is I can define my own trait. Essentially, what I can do for a given vector is I can define a trait, let's call it summable. And remember that vector by itself is a generic type, so I'm going to have my trait as a generic type as well. So I'm going to have a summable of t, which is going to have a function called sum, and it's an instance, it's a method here, and it's going to return the type t. All right, so what's happening here is I'm basically saying that there's going to be a trait summable, and whoever implements it has to be able to calculate their own sum. And then I can take a vector of i32 values, for example, and implement summable of i32. So it would look like something like this: impl summable of i32 for a vector of i32. And here I have to implement this generic method, essentially writing function sum, taking self, returning obviously an i32. That would be the sum of all the elements in the vector. And here things are fairly simple because I make a mutable result of type i32 having the value of 0, and then I go through each of the x values in in myself. Because I'm a vector, I can iterate my own values, and I can actually add them to the result like this. So I can get each of the values and add it up to my my result, and then return the actual result. So as a result of all of this, what I end up having is on my vector of int32 values, which is this vector, I magically get a function called sum, which I myself have written, and I can call this function and calculate the actual sum. And if I now run this, you can see that the sum is equal to 6, which is what we wanted.